Structured Query Language, or SQL, is a database language designed for managing data held in a relational database management system. SQL was initially developed by IBM in the early 1970s, date 1986. The initial version, called SQL, or Structured English Query Language, was designed to manipulate and retrieve data stored in IBM's quasi-relational database management system, System R. Then in the late 1970s, Relational Software Incorporated, which is now Oracle Corporation, introduced the first commercially available implementation of SQL, Oracle V2 for VAX computers. Many of the currently available relational DBMSs, such as Oracle Database, Microsoft SQL Server, MySQL, IBM DB2, IBM Informix, and Microsoft Access, use SQL. In a DBMS, the SQL database language is used to create the database and table structures, perform basic data management chores like add, delete, and modify, and perform complex queries to transform raw data into useful information. In this chapter, we will focus on using SQL to create the database and table structures, mainly using SQL as a data definition language, or DDL. The optional column constraints are null, not null, unique, primary key, and default, used to initialize a value for a new record. The column constraint null indicates that null values are allowed, which means that a row can be created without a value for this column. The column constraint not null indicates that a value must be supplied when a new row is created. Table constraints are identified by the constraint keyword and can be used to implement various constraints described in the following. Identity constraint. We can use the optional column constraint identity to provide a unique incremental value for that column. Identity columns are often used with the primary key constraints to serve as the unique row identifier for the table. The identity property can be assigned to a column with a tiny int, small int, decimal, or numeric data type. This constraint generates sequential numbers, does not enforce entity integrity, only one column can have the identity property, must be defined as an integer, numeric, or decimal data type, cannot update a column with the identity property, cannot contain null values, cannot bind defaults and default constraints to the column. For identity, seed increment. Seed is the initial value of the identity column. Increment is the value to add to the last increment column. Unique constraint. The unique constraint prevents duplicate values from being entered into a column. Both PK and unique constraints are used to enforce entity integrity. Multiple unique constraints can be defined for a table. When a unique constraint is added to an existing table, the existing data is always validated. A unique constraint can be placed on columns that accept nulls. Only one row can be null. A unique constraint automatically creates a unique index on the selected column. Foreign key constraint. The foreign key, or FK constraint, defines a column or a combination of columns whose values match the primary key, or PK, of another table. Values in an FK are automatically updated when the PK values in the associated table are updated or changed. FK constraints must reference PK or the unique constraint of another table. The number of columns for FK must be same as PK or unique constraint. If the with no check option is used, the FK constraint will not validate existing data in a table. No index is created on the columns that participate in an FK constraint. Now let's talk about check constraint. The check constraint restricts values that can be entered into a table. And let's talk about default constraint. The default constraint is used to supply a value that is automatically added for a column if the user does not supply one. A column can have only one default. The default constraint cannot be used on columns with a timestamp data type or identity property. Default constraints are automatically bound to a column when they are created. It can contain search conditions similar to a where clause. It can reference columns in the same table. The data validation rule for a check constraint must evaluate to a Boolean expression. It can be defined for a column that has a rule bound to it. The SQL data manipulation language, or DML, is used to query and modify database data. In this chapter, we will describe how to use the select, insert, update, and delete SQL DML command statements defined as follows. Select, to query data in the database. Insert, to insert data into a table. Update, to update data in a table. Delete, to delete data from a table. In the SQL DML statement, each clause in a statement should begin on a new line. The beginning of each clause should line up with the beginning of other clauses. If a clause has several parts, they should appear on separate lines and be indented under the start of the clause to show the relationship. Uppercase letters are used to represent reserved words. Lowercase letters are used to represent user-defined words. The select statement or command allows the user to extract data from tables based on specific criteria. It is processed according to the following sequence: select distinct items, from tables, where predicate, group by fields, order by fields. Sometimes you might want to focus on a portion of the publishers table, such as only publishers that are in Vancouver. In this situation, you would use the select statement with the where criterion, that is, where city equals Vancouver. These first two examples illustrate how to limit record selection with the where criterion using between. Each of these examples give the same results for store items with between 20 and 50 items in stock. The like keyword selects rows containing fields that match specific portions of character strings. Like is used with car, varchar, text, datetime, and small datetime data. A wildcard allows the user to match fields that contain certain letters. For example, the wildcard province equals N% would give all provinces that start with the letter N. The having clause can be used to restrict rows. It is similar to the where condition, except having can include the aggregate function. The where cannot do this. The having clause behaves like the where clause, but is applicable to groups. In this example, we use the having clause to exclude the groups with the province BC. The insert statement adds rows to a table. In addition, insert specifies the table or view that data will be inserted into. Column list lists columns that will be affected by the insert. If a column is omitted, each value must be provided. If you are including columns, they can be listed in any order. Values specifies the data that you want to insert into the table. Values is required. Columns with the identity property should not be explicitly listed in the column list or values clause. When inserting rows with the insert statement, these rules apply. Inserting an empty string into a varchar or text column inserts a single space. All car columns are right-padded to the defined length. All trailing spaces are removed from data inserted into varchar columns, except in strings that contain only spaces. These strings are truncated to a single space. If an insert statement violates a constraint, default or rule, or if it is in the wrong data type, the statement fails and SQL Server displays an error message. When you specify values for only some of the columns in the column list, one of three things can happen to the columns that have no values. A default value is entered if the column has a default constraint. If a default is bound to the column, or if a default is bound to the underlying user-defined data type. Null is entered if the column allows nulls and no default value exists for the column. An error message is displayed and the row is rejected if the column is defined as not null and no default exists. By default, data cannot be inserted directly into an identity column. However, if a row is accidentally deleted or there are gaps in the identity column values, you can insert a row and specify the identity column value. There are many built-in functions in SQL Server, such as aggregate, returns summary values, conversion, transforms one data type to another, date, displays information about dates and times, mathematical, performs operations on numeric data, string, performs operations on character strings, binary data, or expressions, system, returns a special piece of information from the database, text and image, performs operations on text and image data. Aggregate functions perform a calculation on a set of values and return a single or summary value. As for function descriptions, AVG returns the average of all the values or only the distinct values in the expression. Count returns the number of non-null values in the expression. When distinct is specified, count finds the number of unique non-null values. Count asterisk returns the number of rows. Count asterisk takes no parameters and cannot be used with distinct. Max returns the maximum value in the expression. Max can be used with numeric, character, and date-time columns, but not with bit columns. With character columns, max finds the highest value in the collating sequence. Max ignores any null values. Min returns the minimum value in the expression. Min can be used with numeric, character, and date-time columns, but not with bit columns. With character columns, min finds the value that is lowest in the sort sequence. Min ignores any null values. Sum returns the sum of all the values, or only the distinct values, in the expression. Sum can be used with numeric columns only. One thing that you will most certainly run into at one point or another when working with Microsoft SQL Server or any other relational database management system or RDBMS is blocked processes caused by locks on database objects. But what are database locks and why can they sometimes cause one process to block another? Locking is an integral part of any successful processing of transactions in any good RDBMS. The reason for this is the need for data integrity within the system. One of the important ways RDBMS keeps the integrity of the data stored is by making every transaction pass the acid test, which means it meets the following criteria. Atomic. The transaction performs in an all-or-nothing fashion. Consistent. Transactions are processed in a uniform manner. Isolated. Transactions are properly isolated until they are finished. Durable. The RDBMS will maintain a record of uncompleted transactions in the event of recovery during a failure. The isolation part of the acid test is addressed by locking objects, in most cases one or more rows of data, until the associated transactions are completed. The locking of objects stops all other processes from being able to change these objects until the lock is removed. Blocking is the logical outcome of locks being issued against various objects in a database. If a request is made against an object which has a lock issued against it, then the request is delayed until the lock is removed. The delaying or stopping of a transaction is referred as a block. An example of this would be if request A is attempting to insert a row in table T. Subsequently, before request A completes, request B submits an update on table T. If the row affected by request A is also affected by request B, then a block is encountered, because the row affected by request A has an exclusive lock issued against it for the duration of the transaction. There will always be some level of blocking in an SQL Server database. This is the natural outcome of the goal of 100% data integrity and the resulting need for locks. High levels of blocking or blocks that are not quickly resolved can become a major concern. Blocking can impact a company's ability to keep its data current, and it can also affect the end users of that data, such as clients coming to its website. One of the most common symptoms of excessive blocking is high SQL Server wait counts, which in turn can cause slow response times to requests made on a database. There are a number of ways to locate blocking issues in SQL Server, and in turn, the system process IDs, SPIDs, involved in blocking. If you have the correct SQL Server permissions, here are two of the easiest ways to find them using SQL Server Management Studio. To find blocks using this method, open SQL Server Management Studio and connect to the SQL Server instance you wish to monitor. After you have connected, right-click on the instance name and select Activity Monitor from the menu. SQL Server Activity Monitor 1. Once Activity Monitor has loaded, expand the Processes section. Any processes which are currently in a blocked state will display the SPID of the processes blocking it in the Block By column. In the example as follows, we see the SPID 55 is being blocked by SPID 54. SQL Server Activity Monitor 2. SQL Server System Stored Procedure SP_who2. To find blocks using this method, open SQL Server Management Studio and connect to the SQL Server instance you want to run the stored procedure on. After you have connected, right-click on the instance name and select New Query from the menu. SQL Server SP_who1. Once the new SQL Server query window opens, type the following TSQL statements in the window and execute them. Use master, go, exec sp_who2, go. A list of processes will be displayed, and any processes which are currently in a blocked state will display the SPID of the processes blocking them in the Block By column. In the following example, we see that SPID 55 is being blocked by SPID 54. SQL Server SP_who2. Understanding which queries and processes are causing blocks is important in helping make sure your website is running smoothly and providing the best experience for its users. Blocked processes caused by locks on database objects are a common issue. Locking ensures the integrity of data stored within databases by forcing each executed SQL Server transaction to pass the ACID test, which considers that every transaction must meet the following requirements. Atomicity. A transaction must be either fully completed when executed, or it will not execute at all. Consistency. Transactions must create a new state of data that is valid, or if any failure occurs, it must return all data to the state that was actual before the transaction is executed or started. Isolation. A transaction that is in process of execution and is not committed yet must be isolated from all other transactions. Durability. Committed data must be saved in a way that will maintain data in correct state. if a transaction does not complete in the event of a failure and restart of the system. As part of the acid test, isolation is carried out by locking affects objects, and as such, isolation can affect one or more data rows until the SQL Server transaction that is executed against that object is committed. This means, in practice, that by locking the object, SQL Server will prevent any other process from making any change against the data in that object until the lock is removed, either by committing the change or rolling it back. Imposing the lock over an object will cause any other process that imposes a request against the locked object to wait until the lock is removed, which will delay execution of that process. The state when a transaction is waiting for the lock to be removed or stopped is what is known as a block. SQL Server is designed to work this way, and as such, blocks are not inherently problematic. Therefore, only when a high level of blocks is detected on SQL Server, or in a case in which blocks occurs that require excessive amount of time to be resolved, should it be treated as a potential issue. A practical example of SQL Server blocking is when transaction number 1 is trying to update data in table A, and while transaction 1 is still running and is not completed, transaction 2 tries to place a new lock on table A. If the row that should be deleted is also the row that will be updated by transaction 2, then transaction 2 will encounter a block. This is because transaction 1 has an exclusive lock imposed on the table while the transaction is running. So, how do we identify instances of SQL Server blocking? There are a couple of ways to do this in SQL Server. First is using Activity Monitor, and second is using SQL Server DMVs. Activity Monitor is an SQL Server Management Studio tool that enables users to see details of existing SQL Server connections, and it can be used to show information about the open processes and locks on SQL Server resources. To open Activity Monitor in SQL Server Management Studio, right-click the SQL Server name in Object Explorer and click Activity Monitor. Expand the processes and locate the process that is waiting. Once the process is located, take a look at the Blocked By column to find the process ID that has caused the blocking. Now, when the process that is causing the blocking is identified, it has to be located in the same processes page. Now, when the information about the process that is causing the blocking is found, the user might opt to kill that process or to allow it to run until it completes. To kill the process, right-click on it and select Kill Process. The Dynamic Management View, sys.dm exec request, is used for identifying the SQL Server blocks. It can be used to list currently active blocks by executing the following query. Use master, go, select session ID, blocking session ID, wait time, wait type, last wait type, wait resource, transaction isolated, on level, lock timeout, from sys.dm exec request, where blocking session ID, less than greater than 0, go. In the results, it can be seen which process is blocked, session ID, what process is blocking, blocking session ID, what wait type is involved, and what the wait time of that blocking is, as well as the resources involved. To terminate the blocking session, ID 74 in this case, use the kill command, kill 74, go. Here's a quick tip. Take care when killing a process and make sure that there is a complete understanding of what that process is doing and why it is causing blocks. When a transaction is killed, all data changes made by that process to be rolled back into a previous state. But these native SQL Server methods can be used only for detecting and identifying active blocks. In many situations, when a block is detected and identified, it is important to know whether this constitutes normal behavior and whether it occurs rarely or only once. Without such information, it is not possible to perform required troubleshooting, simply because no historical data about blocks are available, such as blocking frequency and the extent of blocking. This is why a third-party performance monitoring tool like Apex SQL Monitor can be helpful. Apex SQL Monitor is a performance monitoring tool that can track wait statistics on the individual query level, store data in a central repository database to ensure easy access to historical information. To use the Apex SQL Monitor to identify the SQL Server blocks, select the SQL Server instance in the left pane that you have to troubleshoot. Go to the Query Weights tab by selecting the charts in the main menu. Now select the Query Weights tab and check the Block Queries radio button. If there are any blocked queries, they will be listed in the grid and displayed in the chart. By expanding the specific query on the plus sign at the beginning of the row, details about that query block will be displayed. Here, the most important information is related to the blockers section. Information about SPID number of the process that is causing the block, and resources involved in this block, wait resource. For better understanding of how to decipher the resource, please refer to the Microsoft article, INF, Understanding and Resolving SQL Server Blocking Problems. Every block is actually a situation when one process is waiting on another process to release the lock, so SQL Server will register that wait using the LCK_M_XXX wait type. Depending on what the blocked query is waiting for, this query wait will be displayed. By mouse clicking on the wait type name, helper information about the wait type and advice on resolution with additional links to resources about that wait type will be displayed. So now it is easy for the user to get detailed info about not only the current blocking, but also about all blocks that occurred in the monitored SQL server. Users can now easily analyze how often the specific query has been blocked and by what processes. To check the history of the blocks for that particular query, access the History tab. As it can be seen from the image, this query has been blocked only once during the day by process SPID 74. But if we check the other blocked queries, it can be seen that it is always the SPID 74 process that is involved in all blocks. This seems like actionable information that could be further investigated. In addition, it is good advice to check the previous days for blocks that occurred in order to better understand when, why, and how it occurred. To do that, select the previous day, for example, from the date picker in the Query Weights tab. The SPID 72 was blocked 4 times during the previous day, and after taking a closer look at the details, it can be seen that SPID 72 was itself blocked by SPID 74. Based on this, there is reliable evidence that it is not just a rare case of blocking, but that blocking occurs regularly and is caused by SPID 74. Therefore, SPID 74 and the query behind that process ID is causing the blocks, and the SPID 74 query must be investigated more closely. In order to track the blocked query or queries for easier and faster inspection in the future, assigning an alias to that query, example, blocked update table X, will ensure that the query will be noticed easy if the situation repeats itself. To do that, go to the Rename tab. Insert the desired name, descriptive or names according to company convention are recommended, and then save the change. Data aggregation is any process in which information is gathered and expressed in a summary form for purposes such as statistical analysis. A common aggregation purpose is to get more information about particular groups based on specific variables such as age, profession, or income. Sometimes a class type really represents a collection of individual components. Although this pattern can be modeled by an ordinary association, Its meaning becomes much clearer if we use the UML notation for an aggregation. Example: a small business needs to keep track of its computer systems. They want to record information such as model and serial number for each system and its components. A very naive way to do this would be to put all of the information into a single class type. You should recognize that this class contains a set of repeated attributes with all of the problems of the phone book pattern. You could fix it as we show here. Here you have the incorrect model with improvement. System Components Class Diagram. The improved model will accommodate the addition of more types of components, like a scanner, perhaps, a system with more than one monitor or printer, or a replacement component on the shelf that doesn't belong to any system right now. But UML allows us to show the association in a more semantically correct way. In the better model with UML aggregation, System Components Class Diagram, the system is an aggregation of components. In UML, aggregation is shown by an open diamond on the end of the association line that points to the parent aggregated class. There is an implied multiplicity on this end of 0, 1, with multiplicity of the other end shown in the diagram as usual. To describe this association, we would say that each system is composed of one or more components, and each component is part of 0 or 1 system. Since the component can exist by itself in this model without being part of a system, the system name can't be part of its PK. We'll use the only candidate key, type, MFGR, model, SN, as PK, since this class is not a parent. The system name, just an FK here, will be filled in if this component is installed as part of a system. It will be null otherwise. Now let's talk about System Components Relation Scheme. In UML, there is a stronger form of aggregation that is called composition. The notation is similar, using a filled-in diamond instead of an open one. In composition, component instances cannot exist on their own without a parent. They are created with or after the parent, and they are deleted if the parent is deleted. The potential of the internet to consolidate and manipulate information has a new application in data aggregation, also known as screen scraping. The internet gives users the opportunity to consolidate their usernames and passwords, or PINs. Such consolidation enables consumers to access a wide variety of PIN-protected websites containing personal information by using one master PIN on a single website. Online account providers include financial institutions, stockbrokers, airline and frequent flyer and other reward programs, and email accounts. Data aggregators can gather account or other information from designated websites by using account holders' PINs and then making the user's account information available to them at a single website, operated by the aggregator at an account holder's request. Aggregation services may be offered on a standalone basis or in conjunction with other financial services such as portfolio tracking and bill payment provided by a specialized website, or as an additional service to augment the online presence of an enterprise established beyond the virtual world. Many established companies with an internet presence appear to recognize the value of offering an aggregation service to enhance other web-based services and attract visitors. Offering a data aggregation service to a website may be attractive because of the potential that it will frequently draw local business data aggregation. When it comes to compiling location information on local businesses, there are several major data aggregators that collect information, such as the business name, address, phone number, website, description, and hours of operation. They then validate this information using various validation methods. Once the business information has been verified to be accurate, the data aggregators make it available to publishers like Google and Yelp. When Yelp, for example, goes to update their Yelp listings, they will pull data from these local data aggregators. Publishers take local business data from different sources and compare it to what they currently have in their database. They then update their database with what information they deem accurate. Financial institutions are concerned about the possibility of liability arising from data aggregation activities, potential security problems, infringement on intellectual property rights, and the possibility of diminishing traffic to the institution's website. The aggregator and financial institution may agree on a data feed arrangement activated on the customer's request, using an Open Financial Exchange or OFX standard to request and deliver information to the site selected by the customer as the place from which they will view their account data. Agreements provide an opportunity for institutions to negotiate to protect their customers' interests and offer aggregators the opportunity to provide a robust service. Aggregators who agree with information providers to extract data without using an OFX standard may reach a lower level of consensual relationship. Therefore, screen scraping may be used to obtain account data. But for business or other reasons, the aggregator may decide to obtain prior consent and negotiate the terms on which customer data is made available. Screen scraping without consent by the content provider has the advantage of allowing subscribers to view almost any and all accounts they happen to have opened anywhere on the internet through one website. Over time, the transfer of large amounts of account data from the account provider to the aggregator's server could develop into a comprehensive profile of a user, detailing their banking and credit card transactions, balances, securities transactions and portfolios, travel history, and preferences. As the sensitivity to data protection considerations grow, it is likely there will be a considerable focus on the extent to which data aggregators may seek to use this data either for their own purposes or to share it on some basis with the operator of a website on which the service is offered or with other third parties, we users of the service to the hosting website. There are two primary processes: 1. Transaction management, and 2. Concurrency control in database management systems. Transaction management, or TM, handles all transactions properly in DBMS. Database transactions are the events or activities such as series of data read or write operations on data objects stored in database system. Larson, Blanes, Jaconu, Friedman, Patel, and Zwilling, 2011. Concurrency control, or CC, is a process to ensure that data is updated correctly and appropriately when multiple transactions are concurrently executed in DBMS. Connolly and Begg, 2015. In general, concurrency control is an essential part of TM. It is a mechanism for correctness when two or more database transactions that access the same data or data set are executed concurrently with time overlap. According to wikipedia.org, if multiple transactions are executed serially or sequentially, data is consistent in a database. However, if concurrent transactions with interleaving operations are executed, some unexpected data and inconsistent result may occur. Data interference is usually caused by a write operation among transactions on the same set of data in DBMS. For example, the lost update problem may occur when a second transaction writes a second value of a data content on top of the first value written by a first concurrent transaction. Other problems such as the dirty read problem, the incorrect summary problem are also identified in the Connolly and Beggs textbook. There are two main kinds of concurrency control mechanisms: the pessimistic or conservative concurrency control and the optimistic concurrency control. The pessimistic concurrency control delays the transactions if they conflict with other transactions at some time in the future by locking or a timestamping technique. According to Kung and Robinson, 1981, the optimistic concurrency control that assumes that the conflict is rare allows concurrent transactions to proceed without imposing delays to ensure serializability, then check conflict only at the end when a transaction commits. Notice that there is another mechanism, semi-optimistic technique, which uses lock operations in some situations if they may violate some rules, and does not lock in other circumstances. Both pessimistic and optimistic concurrency control mechanisms provide different performance. Example, the different average transaction completion rates or throughput depending on transaction types mix, computing level of parallelism, and other events. According to Vallejo, Sanyal, Harris, Vallejo, Beyvide, Unsal, Valero, 2011, there is a trade-off between the concurrency control techniques. Their pros and cons are shown as follows. For pessimistic concurrency control, the strength is guarantee that all transactions can be executed correctly. Data is properly consistent by either rolling back to the previous state, abort operation, or new content, commit operation, when the transaction conflict is cleared. Database is relatively stable and reliable. Its weakness is transactions are slow due to the delay by locking or time-stamping event. Runtime is longer. Transaction latency increases significantly. Throughput, or the amount of work, example read, write, update, rollback operations, etc., is reduced. For optimistic concurrency control, the strength is transactions are executed more efficiently. Data content is relatively safe. Throughput is much higher. Its weakness is there is a risk of data interference among concurrent transactions since transactions conflict may occur during execution. In this case, data is no longer correct. Database may have some hidden errors with inconsistent data. Even conflict check is performed at the end of transactions. Transactions may be in deadlock that causes the system to hang. Many users often encounter the data interference issues in database management systems in stock markets. The simple example addresses the inconsistent data issue as shown as follows. Multiple analysts or investors from Fidelity Investments, LLC, access a client's fund in a database for stock trading from either Dow, bonds, or mutual funds. Both analysts A, B, perform some transactions to transfer some amount of money to buy stocks from different funds for their daily works. In this scenario, the nested transaction is used in database. At scheduled step T7, a transaction manager faces inconsistent data. That is $800 or $1,000 in the client's balance. The operating system can execute either thread A for a balanced result of 1,000 or thread B for a balanced result of 800. Either case, the balance content is incorrect. For pessimistic technique, the transaction B may be delayed for a long time or in a deadlock. For optimistic technique, it goes through with incorrect data in the database. Furthermore, the micro-execution of the software threads is unknown, ambiguous, and out of control. database is in the unknown state. Java Database Connectivity, or JDBC, is an application programming interface, or API, for the programming language Java, which defines how a client may access a database. It is Java-based data access technology and used for Java database connectivity. It is part of the Java Standard Edition platform from Oracle Corporation. It provides methods to query and update data in a database and is oriented towards relational databases. A JDBC to ODBC bridge enables connections to any ODBC accessible data source in the Java Virtual Machine, or JVM, host environment. Sun Microsystems released JDBC as part of Java Development Kit, or JDK 1.1, on February 19, 1997. Since then, it has been part of the Java Platform Standard Edition, or Java SE. The JDBC classes are contained in the Java package java.sql and javax.sql. Starting with version 3.1, JDBC has been developed under the Java community process. JSR 54 specifies JDBC 3.0, included in J2SE 1.4. JSR 114 specifies the JDBC row set additions, and JSR 221 is the specification of JDBC 4.0, included in Java SE 6. JDBC 4.1 is specified by a maintenance release 1 of JSR 221 and is included in Java SE 7. JDBC 4.2 is specified by a maintenance release 2 of JSR 221 and is included in Java SE 8. The latest version, JDBC 4.3, is specified by a maintenance release 3 of JSR 221 and is included in Java SE 9. JDBC allows multiple implementations to exist and be used by the same application. The API provides a mechanism for dynamically loading the correct Java packages and registering them with the JDBC Driver Manager. The Driver Manager is used as a connection factory for creating JDBC connections. JDBC connections support creating and executing statements. These may be update statements, such as SQL's create, insert, update, and delete, or they may be query statements, such as select. Additionally, stored procedures may be invoked through a JDBC connection. JDBC represents statements using one of the following classes. Statement. The statement is sent to the database server each and every time. Prepared statement. The statement is cached and then the execution path is predetermined on the database server, allowing it to be executed multiple times in an efficient manner. Callable statement. Used for executing stored procedures on the database. Update statements such as insert, update, and delete return an update count that indicates how many rows were affected in the database. These statements do not return any other information. Query statements return a JDBC row result set. The row result set is used to walk over the result set. Individual columns in a row are retrieved either by name or by column number. There may be any number of rows in the result set. The row result set has metadata that describes the names of the columns and their types. There is an extension to the basic JDBC API in the javax.sql. JDBC connections are often managed via a connection pool rather than obtained directly from the driver. Host database types, which Java can convert to with a function. When a Java application needs a database connection, one of the driverManager.get connection methods is used to create a JDBC connection. The URL used is dependent upon the particular database and JDBC driver. it will always begin with the JDBC protocol, but the rest is up to the particular vendor. JDBC drivers are client-side adapters installed on the client machine, not on the server, that convert requests from Java programs to a protocol that the DBMS can understand. Commercial and free drivers provide connectivity to most relational database servers. These drivers fall into one of the following types. Type 1, that calls native code to the locally available ODBC driver. Note, in JDBC 4.2, JDBC ODBC bridge has been removed. Type 2, that calls database vendor native library on a client side. This code then talks to database over the network. Type 3, the pure Java driver that talks with the server-side middleware that then talks to the database. Type 4, the pure Java driver that uses database native protocol. Note also a type called an internal JDBC driver, a driver embedded with JRE in Java-enabled SQL databases. It is used for Java stored procedures. This does not fit into the classification scheme above, although it would likely resemble either a Type 2 or Type 4 driver, depending on whether the database itself is implemented in Java or not. An example of this is the KPRB, or Kernel Program Bundled driver, supplied with Oracle RDBMS. JDBC:default:connection offers a relatively standard way of making such a connection. At least the Oracle database and Apache Derby support it. However, in the case of an internal JDBC driver, the JDBC client actually runs as part of the database being accessed, and so can access data directly rather than through network protocols. Sources. Oracle provides a list of some JDBC drivers and vendors. Simba Technologies ships an SDK for building custom JDBC drivers for any custom or proprietary relational data source. CData Software ships Type 4 JDBC drivers for various applications, databases, and web APIs. RSS Bus Type 4 JDBC drivers for applications, databases, and web services. DataDirect Technologies provides a comprehensive suite of fast Type 4 JDBC drivers for all major databases they advertise as Type 5. IDS Software provides a Type 3 JDBC driver for concurrent access to all major databases. Supported features include result set caching, SSL encryption, custom data source, DB Shield. OpenLink Software ships JDBC drivers for a variety of databases, including bridges to other data access mechanisms, example ODBC, JDBC, which can provide more functionality than the targeted mechanism. JDB Access is a Java persistence library for MySQL and Oracle, which defines major database access operations in an easy, usable API above JDBC. JNet Direct provides a suite of fully Sun J2EE certified high-performance JDBC drivers. JDBCR4 is a service program written by Scott Clement to allow access to JDBC from RPG on the IBM I. HSQLDB is a RDBMS with a JDBC driver and is available under a BSD license. Schema Crawler is an open-source API that leverages JDBC and makes database metadata available as plain old Java objects, or POJOs.